Okay, ladies and gentlemen, welcome to the fifth lecture on DSP EC 393. In today's lecture, we shall be solving some problems on continuous time Fourier transform. Okay, in the first problem, we are to determine the Fourier series, Fourier transform of the given aperiodic signal x of t e to the power minus at u of t. Okay, so let's go to the solution. From the direct transform equation, we know that x of j omega equal to an integral which goes from negative infinity to infinity x of t e to the power minus j omega t dt. Now then, x of j omega will be equal to minus infinity to infinity, and x of t is given as e to the power minus at u of t times e to the power minus j omega t dt. Now, before going any further, u of t is called a unit step function and is essentially referred to as this function, where u of t is the time axis. U of t goes like this. For all positive values of t, u of t is 1. Now, moving forward, we write down as the integral 0 to infinity e to the power minus at u of t. Notice that the integral here has changed from minus infinity to 0 because there will be no u of t. If we multiply any function with u of t, that means the negative part of this e to the power minus at, when multiplied with u of t, the negative part will become 0, as there is no signal in the negative part of that of u of t. So, taking integral in the negative side to minus infinity, it doesn't prove to be useful in our case. So, we can simply change the limit from negative infinity to infinity, that is negative infinity to infinity, such that it becomes 0 to infinity. Rest of the integral remains the same, e to the power minus j omega t dt. Okay, now we can expand this as follows: 0 to infinity e to the power minus t, taking minus t as common, a plus j omega dt. Just simply multiplying these two terms. Now, so x of j omega will become the integration of e to the power something is e to the power something. So the integrand will be e to the power minus t a plus j omega, and since there is a coefficient multiplied to the integral operator, to the integral variable, so we can simply divide it. So this becomes minus a plus j omega, and the limit of course from 0 to infinity. Now taking this constant term out of the expression is -1 a plus j omega. This becomes e to the power, when t becomes infinity, this whole term becomes infinity. So this becomes negative of infinity, since there is a negative sign, and minus when t becomes 0, so this whole term also becomes 0, e to the power 0. Now e to the power negative infinity is obviously 0, because if we look closely, the curve of e to the power x is something like this. So this curve will meet the x-axis at the point negative infinity, and the value will be 0, and e to the power 0 is of course 1. So multiplying this -1 with this -1, we get 1 over a plus j of omega. So the required Fourier transform of the given function x of j omega will be a plus j omega inverse. Now if we want to solve for the phase and magnitude of this plot, we have to determine modulus of x, which is the magnitude plot, will be equal to 1 over root over a squared plus omega squared, and consequently the phase will be angle of j omega, which will be equal to tan inverse angle of, we can write 1 as 1 plus 0 j, and the lower half a plus j omega, and this becomes tan inverse. And in case of angles in phasor calculation, as you can remember, if the vectors are given in a division form in the angle domain, it will be subtracted from one another. So the numerator, angle of the numerator will be tan inverse y by a, that is 0 by 1, and the denominator will be subtracted from the angle of the numerator, that is tan inverse omega by a. Now then, returning back to the magnitude plot, for this expression, when a equals to 1, then x of j omega becomes 1 over root over 1 plus omega squared, and the plot of root over 1 plus omega squared is like this. And similarly, when a equal to -1, the plot will become somewhat like this, and this highest value will always be 1. So this is the magnitude plot of x of j omega, and this goes to omega. Now in the phase plot, when angle of x of j omega equals to tan inverse 0 is 0, so all we remain with this term, omega by a. So when omega equals to infinity, then angle of x of j omega will be equals to tan inverse of infinity, which is pi by 2. Again, when omega is negative infinity, x of j omega will be negative pi by 2. And when omega equals 0, then x of j omega will be tan inverse 0, that is equal to 0. So the phase plot will look like, for the negative values, this will be negative omega because there is a minus, and here it will be positive pi by 2. This is negative pi by 2. Sorry, this will be positive pi by 2. Okay, let's see, for negative value of omega, for omega to be negative infinity, we get minus tan inverse minus infinity, which is equal to pi by 2. And for positive value of omega, this becomes negative pi by 2. So the plot will be something like a tan curve, which is like this, and this value will be pi by 2, and this over here will be negative pi by 2, and at 0 the value will be 0. So this is angle of x of j omega. So I hope you understand this problem. We have found out the Fourier transform, the magnitude plot and the phase plot. Now let's move to the next problem. Okay, now this problem, we are to determine the Fourier transform of x of t, where x of t equals e to the power negative a multiplied by the absolute value of t. Now then, before going into the solution, what does this plot eventually looks like? This plot will look like, for the negative value of t, that is for t greater than 0 in the positive axis, this will look like something like this. Because if you can remember that e to the power something, e to the power x is a rising curve, and consequently e to the power negative x is a decaying curve. So in the positive value of t, this modulus of t becomes positive, and multiplied with negative of a, this becomes a decaying curve. Similarly, for the negative value of t, we will simply get the mirror of this curve, which is like this, and this value will be equal to 1, x of t, t. So simply we can write x of t to be equal to e to the power minus at when t becomes more than 0, for t greater than 0, and e to the power at when t is less than 0, and there is a discontinuity at t equal to 0, e to the power, 1, value will be 1, because when t equal to 0, e to the power at becomes 1 at t equals to 0. So essentially this is the curve for the given expression. Now Again, from the direct transform, we know x of j omega will be equal to negative infinity to infinity x of t e to the power minus j omega t dt. Now, for expanding this expression, for negative infinity to 0, for this part, the equation is this one. X of t will be equal to this. So, from negative infinity to 0, x of t becomes e to the power at e to the power minus j omega t dt. And for the positive side, this becomes 0 to infinity, and the term becomes e to the power minus at e to the power minus j omega t dt. Now multiplying these two terms, negative infinity to 0 e to the power t a minus j omega dt plus 0 to infinity e to the power minus t multiplied by a plus j omega dt. Now integrating these two expressions, we get e to the power t a minus j omega divided by the coefficient which is multiplied to the integral variable a minus j omega, and the limit of course is negative infinity to 0. Similarly, for the second expression, this becomes e to the power minus t a plus j omega negative of a plus j omega, and the limit of course is 0 to infinity. Now plugging in the limits in this expression, when t becomes 0, e to the power 0 becomes 1. So taking this constant term out, is 1 minus j omega. For the value of 0, e to the power 0 is 1. And for the value of negative infinity, as we have shown earlier, the value becomes 0. Similarly, for this expression, if we take the constant term out, minus plus j omega, this becomes e to the power, when t is equal to infinity, e to the power negative infinity is 0, and when t equals to 0, e to the power 0 is 1. Hence, multiplying these two terms with the coefficients, we get 1 over a minus j omega plus 1 over a plus j omega. Now simplifying this fractional addition, x of j omega will become a plus j omega a minus j omega divided by a squared minus j omega squared. This j omega cancels out, 2a over a squared, and j squared is equal to negative of 1 when multiplied with this negative sign becomes positive, and omega squared remains as it is. So then, the required Fourier transform is x of j omega equals to twice a squared plus omega squared. This is our required answer. Now in the next example, we are to determine the Fourier transform of x of t, which is equal to delta of t. Now then, what is the delta function or the unit impulse function? This axis is t. Now delta of t will be such a function that at the point 0 the value is 1 and everywhere else it is 0. So this is the physical representation of a delta function, or otherwise known as the unit impulse function. So now if we move on to the solution, where we know from the direct transform x of j omega, which is equal to negative infinity to infinity x of t e to the power minus j omega t dt, and of course x of t will be negative infinity to infinity. X of t is here delta of t e to the power minus j omega t dt. So then x of j omega will be equal to now if you look very carefully, as I've said earlier, the value of delta t is only present at the point 0, where t equals to 0. Only then we can get a value of delta of t. Every place else it will be what? It will be 0. So we can simply contract the integration and write this to be e to the power minus j omega t dt, omega t times 1, because we are to integrate for this value. That means, in strictly mathematically speaking, we are to determine the area of this line, and this exists only at one point. So integrating in this direction and this direction is redundant and not necessary. So this becomes 1 times e to the power minus j omega t, and the limit will be t equals to 0, because only for t equals to 0 we get this value, everywhere else it will be 0. This is equal to e to the power, when t equals to 0, this term becomes 0, so e to the power 0 is 1. So then the Fourier transform pair of delta of t will be 1. Now moving on to the next problem, example 4. We are to determine the Fourier transform of x of t, which is equal to 1. Now, what does this graph essentially looks like? If this is the t axis and this is x of t, the curve x of t equals to 1 will be like this. For any value of t, the value will be 1. So if you can remember the Dirichlet conditions, now before going to the Dirichlet conditions, I have shown Dirichlet conditions for the continuous time Fourier series. But you must remember that the Dirichlet conditions always holds for any types of Fourier operation. That is, Dirichlet condition must be true for the CTFS, DTFS, CTFT and DTFT. So from the Dirichlet condition, if you can recollect, the Dirichlet condition says that negative infinity to infinity x of t dt will be less than infinity. That means the curve must be absolutely integrable. So if you want to integrate this area, it is simply not feasible, because there is no closed surface in this direction. There is no closed surface from this point to this point. And hence, using the direct transform, the Fourier transform of 1 cannot be derived. So we need to refer to the properties of the Fourier transform. I hope you understand what I was trying to say. Since this function is not absolutely integrable, we need to refer to a different approach in solving the Fourier transform. So, if you can remember from the duality property, which was discussed in the previous lectures, we get x of t will have if x of t has a Fourier transform of x of j omega, then capital X of t will have a Fourier transform 2 pi times small x of omega. Now, from the previous example, we have seen that the Fourier transform pair of delta of omega, as we have mentioned here, will be 1. So, if this is our x of t and this is our x of j omega, then if we want to replace j omega as 1, then x of t will be equal to 1. X of t, capital X of t, will be equal to 1, which in turn will give twice pi delta negative of omega. Now, how can we write this? Now, x of j omega in this case is 1. And since 1 is a constant and is neither dependent on j or omega, so you can replace x of t to be equal to 1. That is capital X of t to be equal to 1. So capital of X of t is equal to 1. And as for the duality property, the twice pi remains as it is. X of negative omega, x in our case being delta of t, x of t is equal to delta of t, small x of t, that is. So x of omega will be delta of omega, and similarly x of negative omega will be equal to delta of negative omega. So instead of x of negative omega, we can write delta of negative omega. So this can be further simplified twice pi delta of omega, because if you look from this curve over here, x of t and x of negative of t essentially doesn't mean the same point. X of t will be equal to x of negative of t if x of negative of t is the mirror. X of t will be equal to x of negative of t in case of the delta function, because if we mirror this curve along the x-axis, along the y-axis, we get this curve. We get the curve that remains as it is. So delta of omega will be equal to delta of negative of omega. So then if we move forward, we get that the Fourier transform of 1 will be equal to twice pi delta omega. I hope you have understood this problem. It is quite heuristic along this part, but if you look upon closely, it becomes quite clear. Okay, then now moving on to the next problem, what was the previous problem of 4, so this will become 5. So we are to determine the Fourier transform x of t equal to Sgn of t. Now Sgn, or the sign, is otherwise known as the Signum function. Now let us see what a Signum function looks like. If this is the time axis, Signum of t, Sgn of t, will look like this. This is -1, this is 1, 0. So the Signum function is unit step on the right hand side, I mean the positive axis. That means it will have value for all the points in the positive side to be equal to 1, and in the negative side all the values will be equal to -1. So Signum of t can be otherwise written as 1 when t is greater than 0, -1 when t is less than 0. Now if you look closely, Signum of t can be written as twice u of t minus 1. Now how come? You can verify this simply by plotting any point. So when in the positive axis, twice u of t means that u of t is scaled to a factor of 2. So instead of being 1, it will be 2 for all the values. And 1 will have x of t equals to 1 will have a curve like this. So if we subtract this plot from this plot, we can clearly say that in the right hand side, this value is 2 minus 1 will be equal to 1. So in the right hand side, this will be equal to 1. And in the negative, in the left hand side, or the negative axis, we can simply say here the value of 2u of t is 0. So subtracting a -1, so this value from 0 will give us -1. So this part becomes like this, negative of 1. So to recap, 2u of t minus 1, in the positive side 2 minus 1 will be equal to 1, and this will be true for all the points. In the negative side 2u of t is 0, but x of t is still 1 with a negative operator. So 0 minus 1 will be a negative of 1, hence for the negative values it will be minus 1. And this plot over here is similar to that of our Signum plot. So simply, if we can find out the Fourier transform of this expression, we can say it to be equal to the Fourier transform of Signum of t. Now if you remember the differentiation property, the time differentiation, property, we can write dd t of x of t to be equal to twice delta t. Let me expand it a bit. We can write it to be ddt of 2u of t minus 1, and differentiation of negative of 1 is 0. So all we are left with is the 2 becomes constant, ddt of u of t. Now ddt of u of t is equal to delta of t, and this is because in case of u of t, if we want to differentiate u of t, we have to consider this to be infinitesimally divided, and each of this infinitesimal section will be nothing but a delta function. And so for dividing u of t using an infinitesimally small function, infinitesimally small area, we get the delta function. So now this can be written as 2 delta of t. Now then, taking Fourier transform, we can take the Fourier transform on both sides, where if you remember the differentiation property, this will become j omega time differentiation property x of